Hi everyone, thanks for coming. My name is Ayin. I'm the co-founder and chief data scientist at the Foundation for Precision Medicine. And today I'm going to talk about predicting Alzheimer's as an example of how we are able to incorporate AI into healthcare. So I'm going to talk about a little bit about our foundation, so give you a little bit of flavor, why we are picked Alzheimer's to work on, a little bit about methods and tools. People are usually interested in that, and deep learning on EMRs, and putting it all into an application, something that we're working on. By the way, when I say EMR, by a show of hands, how many people think electronic medical records? Okay. How many think Amazon's Elastic MapReduce? Okay. So the point of the talk is really is that we need more people that know both of those, at least in healthcare. So these are the things I'm going to talk about. But before that, I have a video I'm going to show you. Just a couple of minutes. It's about our foundation and what we do, and it's a video that we created with Google. If it comes up. Okay.
My name is Robert Tabbs. And 5.5 years ago, my mother was diagnosed with Alzheimer's. I knew none of the medications were working. The entire time was a downward spiral.
And I also lost my grandfather about 25 years ago to the disease. My family at the time felt like it was already too late to change the trajectory of the disease. And it breaks my heart when I hear the same stories today. The mission for Foundation for Precision Medicine is to bring AI and healthcare together to detect Alzheimer's early.
If you can detect Alzheimer's very early on, that is when the disease is most susceptible to treatment.
The data that we have access to are anonymized electronic healthcare records. We needed a HIPAA-compliant environment, which is why we use Google Cloud.
We're dealing with hundreds of variables on millions of patients, which generate billions of lines of data.
Google Cloud enables us to scale our operations, and with BigQuery ML, we're able to develop machine learning models faster and utilize our entire data. Being a nonprofit, we rely on our volunteers across the US, and Google Cloud really enabled us to do that. We wanted them to be able to apply machine learning on the data and look at trends themselves to empower them to come up with more innovative approaches to change the progression of the disease.
This work is so important to me because it helps us address this devastating illness that has no cure.
I heard somewhere that they said, don't forget that dots on the plot are people. And we really take that seriously. Thanks for watching that. Disclaimer, Google is a very good partner of us, and the products that we use is mostly Google products, but Amazon, AWS, Azure, they all have great products, and I used them before, and they're very similar. So I'm going to talk a little bit about the products that we use and the methods that we use, but use it as a guideline for creating apps and AI applications in healthcare. So really, what is the problem that we're trying to solve? The problem is that there's a gap between the data science and the medical science. Medical science at a pure level is very research-driven, very results-driven, and not necessarily data-driven. The clinical trials are based on 100 people, 150 people, not based on billions of rows. So that's something we think we can help the medical science community. The way they've been running their work is great, but we just think bridging that gap can really resolve some of the problems that they have. So at the foundation, again, we are a nonprofit, and our goal is to bring data science and AI together. We try to develop personalized therapies and personalized medicine that have social impact is what we're trying to do. We have various partners. We work with Stanford, mostly biomedical data science and computer science department there, and working with some professors and some students there. Google is a great advocate of us, and computationally we use their tools. And Mayo Clinic and Yale School of Medicine, we have Alzheimer's researchers there that sort of direct us to where they think it will be more beneficial for us. And also they do a little bit of checks and balances and make sure we are not going on a wrong path, because for us data scientists, everything is just numbers. So for people who have a little bit of context, a biological context behind those numbers is the key, and without that, we could be very lost. So a little bit about Alzheimer's and why Alzheimer's. Again, it's just a disease, pick your own disease. This is just an example of what we are working on. We have two big initiatives. One is in Alzheimer's and the other one is in opioid studies. For another day, I can talk about that. That's also very important. So there are no really treatments to prevent or cure Alzheimer's disease. There's been research in the past 20, 30 years, and unfortunately no big breakthrough. It's the 6th leading cause of death in the US, and it's most expensive single disease. It takes away 1/4 of our entire healthcare budget. So every dollar that comes out of tax goes to healthcare. 25 cents of it goes to Alzheimer's. It's shocking, I know. And 2 in 3 are women. We know some of the factors that contributes to that, but we don't know exactly why, and how much those factors are important. That's something we can quantify when we look at hundreds of thousands of patients and large data sets that I will talk to you about. So generally, healthcare has we've got good progress in other diseases in healthcare. So this is the changes in death rate in the past 2 decades. So people die from HIV 50% less now than they did 20 years ago. And even though obesity is on the rise, but we are getting better in stroke and heart disease and those things. But Alzheimer's disease got 123% worse, so more than double people are dying from it. There are a bunch of factors again. One is that people live longer, and other factors could be contributing to that. But again, what's hard to see is that that has become sort of a bottleneck for some people when they're older. There's some hope. This is very, drug development for Alzheimer's is generally very lucrative when a drug comes out. Unfortunately, most of the drugs fail at the end. But in the past couple of years, we have seen some good traction with some of the drugs that are coming out at Big Pharma. This is a quote by a company. Eli Lilly is a big pharma company, and they said, their drug actually came out and failed in a large clinical trial. It didn't really work, but it did work for a small population of those people who were on early trajectory of Alzheimer's. So looking at that, they decided and they said, the early detection and early diagnosis really matters when it comes to Alzheimer's. And for us data scientists, early detection, prediction, all those things, we think of, okay, we can look at historical diagnoses for thousands of patients, and maybe we can predict that this is going to happen, and that's how we're going to help the pharma company and other places in clinical trials. So really now researchers believe, and this is clinical researchers, not just us, that the early detection is the key, right, to preventing, slowing, and stopping the disease. And traditionally, because they work with 100 patients, small clinical trials, it's hard to do some early detection. When you have thousands of patients, it's much more possible. So we thought, how can we attack this problem? What are the data sets that we need? And in healthcare, if you're in healthcare industry, you know that data is in different silos, and it's very difficult to have all the data in one place. So we went after a bunch of large data sets that we were able to get our hands on, some from universities, some from large hospital systems across the US, some from assisted living facilities for older people. And these are some of the data sets that we were able to get access on. What we call encounter data is when a patient comes to a hospital, and that's the data they get when they visit. Historical diagnosis is very important, medication, and there's some data that we're getting now. There's some genetics data, doctor's notes and those things, and some data that's very difficult to get, like family history. I lost my grandfather to Alzheimer's 25 years ago. Nobody knows. It's not in electronic medical records. Nobody knows about that. So that's hard to get. So I'm going to focus on two data sets that we got. The first one is around 4 million patient records. About 200,000 of them were diagnosed with Alzheimer's in a doctor's office. So for my data scientist, that becomes binary classification problem, right? You have 200,000 people that are Alzheimer's, and there's almost 4 million that know Alzheimer's, and you have a bunch of variables for each, hundreds or more. So that's one data set that I'm going to talk about. The other one was about 2,000 patients that we had brain scans for. Those 2,000 patients. Half of them have Alzheimer's, and the other half were healthy. And these are different data sets. They're not connected, unfortunately. So later on, maybe hopefully 5 years down the road, when you can get data, all the data possible for a patient, somehow we can combine these studies together. And our goal was to alter the course of progression for Alzheimer's. The first thing that we need to do is to collaborate with clinical researchers, because we have no clue what we need to look after. Just looking at correlations in data doesn't cut it in healthcare. So we worked on early detection with structured data, which is that first data. That first data is a bunch of relational data from electronic healthcare records, data such as historical diagnoses, other diseases, procedures, the location of the patient, the location of the hospital, size of the hospital, all those things, hundreds of variables. Second thing that we're working on is early detection of MRI images, so I will show those two. And what we're working on right now is implementing it to an app, so consumers and people can use somewhat like an Alzheimer's prevention app that we're working on. So again, first thing, you really need to gain a little bit of domain knowledge of what you're dealing with. We curated hundreds of clinical papers in the past 30 years. So we look to see what are the trends, what are the things everybody's talking about. So we find out, for example, there are clinical trials that said diabetes is very correlated, or cardiovascular disease is very correlated, and your chances are 50% more, something like that. And we said, okay, well, that's what the small clinical trial is saying. Can we see that effect in our data? Do we see that correlation, right? And just build all those variables that we think are important based on our data from what research has shown. When we think, Alzheimer's is a very complex disease, and it's based on many factors, and what may have gone wrong in the past 30 years is everybody was working on that one factor, and what we're doing differently is combining all those factors, and maybe that way we can get a better algorithm and better way of solving this. And some of these factors, are just correlated. Some of them are causal. Let's say, cardiovascular disease, the blood flow to brain decreases, so maybe that's why some of the neurons die earlier. So some of them can be causal. The tools that we use, again, these are Google Cloud tools. We use BigQuery. It's like Amazon Redshift, I think, and it's basically the table format data. You can query billions of rows in a matter of seconds. I don't know what kind of sorcery they run underneath, but it's insane how fast it is. They released BigQuery ML about a month ago. And that's when you can SQL, query your data, and you can run machine learning right there. And it's somewhat intelligent. It knows what variables are categorical, what are continuous. It does one-hot encoding for you for the categorical variables right there without you doing that. So some things that data scientists have to do manually, that would take a lot of time. It does that. We use, Data Studio is a platform that they have that it's sort of like a Tableau-like platform. It connects to BigQuery. So our researchers really like that because they're able to make their own plots based on billions of rows, and it matters a matter of seconds. It's very fast, and we're actually empowering them to do that themselves, other than we making a plot in a Jupyter notebook and send the plot to that person. The person is like, oh, well, this is not what I was looking for, and we just go back and forth, and it's not really great. We also use a bunch of machine learning things they have on our platform, and Kubernetes engines, just like Docker. We use that for our app. So to just give you a little bit of, so this is, for example, a chart that one of our clinical researchers created because they wanted to look at, if any of these drugs that they were interested, they wanted to look at the populations and see if any drug, have more Alzheimer's patients or not on that drug. So this is Data Studio. They could make different filters, look at different age groups, different drug classes, and those things. And these things they're able to do themselves. So it's great because you want to empower your clinical researchers, so you don't have to do all the work yourself. Our data scientists also can make templates and those things and send it to the people. So here they were just looking at drugs that were posing risk. In terms of deep learning and machine learning, this is what we had in mind. So sort of, this is the vision that we have, that you have electronic healthcare records, and you have a dense deep learning model or whatever on that. Then you have medical image from that person. You have your convolutional neural net model that works on that, and maybe you have some doctor's notes, and you have a word embedding, NLP way of working on it. And if we're able to combine all of those, we think it could be very we could get good results. So today I'm going to maybe talk about the first two. Again, there are two different projects, but at some point we'll be able to combine all those studies. So early detection with structured data. What are the variables that we were looking at? So all those variables that I talked to you about: age, gender, what we call comorbidities, which is the other diseases that are correlated to Alzheimer's disease, historical diagnoses. So patient comes in and they're diagnosed with something, and we use that. Some medications that patients take, we look at some of those medications. So there are some medications that have shown to have adverse effect based on clinical trials. So we looked at those and we saw some correlation that exists. We added to the model. Again, what you're trying not to do is to just have all the variables and just throw it in the model and see what it does. That's not a really efficient way of doing it. Also, we don't just jump into deep learnings. We start with simple algorithms that are not as black box, and maybe you can show that to somebody in a research community and that have done research for 20 years in Alzheimer's and show and see, tell them, hey, these are the variables that my algorithm thinks are important. What do you think? And work your way up from there. So We try different things, SVMs, KNNs, random forest, all those things. The most accurate algorithm actually we came up with was, on this structured data, was a deep learning algorithm that would combine all those algorithms together as a method that's very popular in Kaggle competitions. But it was very computationally expensive, so we had to scale it down, and now we use just a overly dense deep learning algorithm to do that. And what we're trying to get is chances of Alzheimer's for patients in a simple way, 20% chance, 30% chance, something like that. And also contributing factors. So I would tell that person, hey, diabetes, cardiovascular disease, these are the things that are contributing to your chances the most. And some of these things, there's some action that you can take. Maybe you have high cholesterol level, you need to bring that down. So talk to your doctor. Maybe you need to take medication on that. Bring that down. Lower chance for cardiovascular disease, lower chance for Alzheimer's. Those things. And we work with, again, in the medical community to come up with those actionable insight, the things that we can tell the patient that they can do. Because it's a prevention app. It's not just an app that tells you what are your chances. So it would come up with something like this. So if it's like this is a timeline for this patient, this is an actual patient, 64-year-old with some other diseases. So this is now, for example, we would say, chances for Alzheimer's for this patient is very, very high. Chances a lot lower, without diabetes. So maybe, this person can lose weight. And, this person is, 60 years old. So there are things they can still do in the next 20 years that can affect their, health. And even it would say, patients are like this patient. So doctors really love this. Patient take, Domperidone is a very common drug, and there is different dosage. So what happens today is that, doctors don't know what medications to give, what dosage to give. The more dosage you give, it's more potent, but has more side effects. So even a little bit of knowing, what are the chances of Alzheimer's for this patient can maybe help them put them on the dosage that they need. And again, we're not trying to remove the doctor at all. We're just producing, we're trying to make their decision more data-driven. So all we're trying to do, and they love that, and we can even show that, hey, 40% switch to different drug in 4 months. They would love to know that too. Because maybe I just put this patient on that drug to begin with, so that you don't have to switch 4 months later. There are a lot of switching going on right now for Alzheimer's patient. Patient comes in, they give him this drug. 3 months later, patient comes back, they increase the dosage. 4 months later, patient comes back, they give him a different drug. That's just what's going on right now. Again, it's not very efficient at all, and we can help with that. So a little bit of, so this is a cooler part of what we're working on is Alzheimer's detection with using MRI images. So what we were trying to do here, and again, we had only 2,000 patients on this. Half of them were healthy, half of them were not. And what you see here, this is a healthy brain, and this is like an Alzheimer's brain. And what we're trying to do, our goal was to see if we can somewhat at least see the things easily, that the expert sees it right away. Can we detect those automatically? And that would be something that would, be implemented into that app. So enlarged ventricles here compared to this, this is something that an expert would see right away and say, okay, well, that doesn't look good. Shrinkage in the hippocampus here. So hippocampus is where the memory is stored. So shrinkage there. Also would say this person may have Alzheimer's. So we wanted to know if the model can at least see those. And overall shrinkage too. So that's what we're working on. The method that we use is transfer learning or fine tuning. And the reason for that is we only have, again, 2,000 patients. I think we have longitudinally, we have maybe up to 5,000 images for those patients. And that's very hard to create a deep learning algorithm on that. If you have millions of images like ImageNet, that's great, do that. But if you don't have that, transfer learning actually works pretty well. So just to give you a flavor of what it is, this is your deep learning algorithm. Really, the first few layers, all it's doing is to extracting those features, extracting edges, and then from edges, extracting shapes, and all those things. At the very end, well, not very end, but here, it comes up with a bunch of features, basically an abstract representation of that image to a computer in a form of a matrix, right? And based on that, it matches it to your target. So I got this many features, I got Alzheimer's, I got these different features, I got non-Alzheimer's, and here's what you're training it. So transfer learning is using this part that's being done in some other model, models by Google or Microsoft and those companies, and you use that. You use that as a frozen layers. You don't change those, but you change this part. So you feed it classified images that are labeled, and it will try to match it, and it works pretty well. The fine-tuning, the difference between fine-tuning and transfer learning is that fine-tuning, you have more images, let's say 20,000 images, 30,000 images, it starts training these latest layers too. You will work your way back. It works much better this way compared to if you just have a deep learning model on your 5,000 images. So it's actually pretty fascinating and works pretty well. So the results that we got for this particular one, it's kind of interesting. So these are, on the left, predicted Alzheimer's. These are predicted non-Alzheimer's. You see true positive and false positives and those things, and the chance that the algorithm is giving. And right away, you kind of see, on this side, you see larger ventricles right here, compared to these. It does make mistakes. It thinks that this one, an Alzheimer's one, a healthy one, but that person does have an Alzheimer's. But generally, you see that, and generally, you kind of see the shrinkage of the brain too. These were fuller brains. It's fascinating how it works. And a little bit more images, 1,000 more images, 100 more images makes things a lot more accurate. So for this one, right now what we have is about 0.8 for specificity and sensitivity, which is not bad. In the medical community, 0.85, and those two are pretty good. That's you can make a medical device out of that and get FDA approval. So we were pleasantly surprised how good this works. So what are we doing with all of these things? So, and this is mostly not the image part, just the structured data. So we are putting all these things into an app. This is just screenshots of an app that we're working on. It's not out yet, but hopefully be out in the next couple of months. So the patient comes in and put their medications in, put their diseases in, lifestyle factors, if they're smoking, if they have a family history, and this would, produce some sort of chances of Alzheimer's, also the factors that are contributing, and recommendation on the things that person can do. Because right now, what they tell you is, go play Sudoku or something. That's like all you can do. So this would give that person, much more things to do, and it's a starting point to talk to a doctor, because a lot of these factors the doctor doesn't have, and they don't see it in their monitor, unfortunately. They don't know if you're a smoker or not, because that data is somewhere else and it's not connected to this data set that they're pulling data from, and they don't know your family history and education history. They have to ask you and all those things. So this thing will give you a little bit of information that you need. Somewhat similar to, before you go in doctor, a lot of people go and Google things around and see, what are the things that they should be looking or asking the doctor. And that's what we're keeping it now. Later on, if this is very accurate, we can get FDA approval for it, and we can actually implement it in the doctor's office so they can use it. But this is the way that we have started working on it right now. And one last thing that I wanted to say was Google Cloud actually have this is a little nugget. As of a month ago, they have this thing called Data Solutions for Change. So if you're a nonprofit, you can actually get funding and credit to work on your data on Google Cloud. I believe they give you about $30,000 of Google credit, and they give you a bunch of training sessions and all those things. Again, if you're a nonprofit, I think at this point your chances are very high to get accepted to the program. And that's pretty much what I had for today. Thank you very much for coming. I'll take all your questions now. Thank you.
So the images that you had, were they like from diagnosis? Because you talk about early detection, and let's say if the disease has already manifested itself, and you could detect in the image, from a classification perspective, it's a simpler problem. But detecting early then is harder because you might not have all the signals early. So did you have the longitudinal sort of multiple MRI per patient, and are you able to also find the signal as to how it develops, or were you only looking into confirmed diagnosis versus confirmed non-diagnosis?
Yeah, that's a good question. We do have longitudinal data for some of those patients, and even some of them, there's a score attached to it. Some of them are more full-blown and less full-blown. It was hard for the algorithm to detect between early Alzheimer's patient and late Alzheimer's patient. So what we're using now is just yes or no binary classification. But if you have more images, that would be much better. Again, right now, the way it is now, there is a score attached to how full-blown your Alzheimer's is. That's what the diagnosis that they're given in a hospital or a patient's office, doctor's office. But that's a good question. We just need more data for that.
On that topic of how are you going about collecting additional data? What's your strategy for that?
Partnering with research centers, so large medical facilities and large universities sit on a lot of medical images. The medical image is a little bit more difficult than just electronic records, and the reason for that is it's more expensive, and sometimes is not very much connected to the rest of the healthcare records. But partnering with, so we're right now working with Mayo. We started working with UCLA. So those, hospitals, hospital system, university system have a lot of data, and we show up with something that works a little bit, and we say, hey, if you have more images, this thing would work a lot better. We are a nonprofit, so that helps a ton, because these people get bombarded by vendors and app companies all the time. So that does help. That sort of has been our strategy.
You also talked about how you have genetic data that's included in the model suggested. How were you able to leverage that? Was it advantageous? I understand there's genetic markers for Alzheimer's.
So that's the data that we are getting access to now, and again, that's even harder for that data to be connected to the rest of the healthcare record. So you do get genetics data for 100 patients, and it's not really helpful. But there are a lot of, if you search in literature, there's some factors that you can get. They say, if you have a family history, of Alzheimer's, your chances are 5% more, things like that. We try to incorporate that into our model right now. Interestingly, though, for the MRI images, we did have genetic factors for those patients. We did. For the MRI images, we did, but not the rest of the healthcare records that we were working on. So, and preliminary, what we see in data is the genetics factors are a factor, but it's not the biggest factor.
Have you also thought about including in your app questions about diet and lifestyle?
Yeah, we do have that. A moderate diet, healthy diet, because exercise helps, healthy diet helps. Again, weight and other factors help or hurt. So we use those lifestyle factors, and there's actually a good amount of literature that we can use to incorporate that to our model.
One last question, I don't want to take any more time. What's the theoretical limit from your perspective on how early you can detect, and how would that drive how early we should get this into, say, preventative health and screenings?
Yeah, so the goal is like 5 years in advance to be able to do that, because that's actually can do stuff. Right now, what we have based on the data we have is very snapshot. It's like, based on the information we have from you today, this is what we can say, which is not great. But there's some things that we can do. For example, there's many models to predict diabetes later on in life. And those models are work very well. So we're trying to see if we can incorporate those in our algorithm, get the chances that this person is going to have diabetes in 5 years from now, use that in our algorithm. It's just a more intensive work that we have to do. But again, goal really is 5 to 10 years in advance, because otherwise, there's not much the person can do.
You looked at anybody using gene expression data as a signal?
There are many work that's been done in universities that actually very good. There's the Genomics Center at Stanford is doing really good work on that. But the thing is, we are trying to make a product or make an app that is usable for everyone. So if only 0.1% of people who would use the app have done genetics testing, we're not going to be able to really use that. So the things that we find in electronic health records are the things that are really available, and we're trying to use that information, because anything that you find based on that information, you can have it into app, you can have it into model, and that works better. But if we get more patient data, we can do more of that. Yeah, so data we have is 10 years for those 4 million patients. So we know what happened 10 years ago, and now this person have Alzheimer's. With technique that we have a training and testing data set, we try to predict if that happened 10 years down the road. That's how we are working on that. A good way would be to have this thing actually implemented as a decision support tool, is what it's called, for doctors in doctor's office, and whatever they decide at the time, it gets recorded, and later on, maybe hopefully there's a feedback. The biggest problem with healthcare, other than the fact that the data is in different silos, is that there's no feedback loop. Patient leaves, and we don't know they didn't come back because it worked, or they didn't come back because it didn't work. So. So for the first one is the data was in flat files, 4 million patients, basically CSV files. So we load all those into BigQuery. There are relational data sets. So one data set is all procedures, one data set is cost related, one data set is about the doctor and the facility, all those things. Does that answer your question? Uh-huh. I believe it's, what is it, NII format is the format that most think so. Very early on, we turned it into JPEG. And for that, for 2,000 patients that we had, it was actually a 3D of an image of brain. So you can get different slices. The early slices and late slices don't have as much information, but mid slices they do. So we actually try to use those slices to give more images, similar to when you get an image and you flip it for the algorithm to use. That's what we've done. We change it, we turn it into JPEGs right away. There's a couple of models we use. I think the one that we're using now is a later version of Inception, not Inception V3, but it's a better version of that. I think it's the one that's giving the best results. We are doing transfer learning, yeah. Yeah. One more question. That's a very, very good question. So in the literature right now, there's a lot of research right now that says a lot of Alzheimer's comes from sleep apnea and sleep problems. Turns out when you're sleeping, these plaques in the brain gets washed out. And if it doesn't, those plaques sit on neurons and kill the neurons. Funny thing is, when we looked at the data, we saw a strong correlation between sleep medications and Alzheimer's. So we're like, oh man, these are the medications. But then we find out, okay, well, maybe the problem was sleep problems, not the medication. That's what it was more correlated. We don't have that now, but in the app, that's what we're asking people. Again, that's the data. You don't have that in electronic healthcare records or medical images or anything like that, which is, not great. Yeah. Yeah. So wearables can help. Yeah. Once you integrate all these things in a phone, I think we're able to get those. Well, thank you very much. I'll be out. If you have more questions, come to me, talk to me. If you have questions about nonprofit and get it off the ground, that's something I worked on. And if you're trying to get involved in this, let me know. I'll be outside. Thank you.